Does a Turing machine accept any strings at all? Or is the language defined by a given Turing machine the empty language? That problem is undecidable, and in this video we'll give a proof of that using our technique of reduction. Let's restate that. Does a Turing machine accept any string at all? Well, this is undecidable, and in this video we're going to show why it's undecidable. More formally, here is a description of the problem. E for empty, TM. Is the language empty? It's given a string, and that string is part of the language if M describes a legitimate legal Turing machine and that Turing machine accepts no strings. In other words, the language defined by M is the empty language. And our theorem is that that language is undecidable. And here's an outline of our proof. We're going to assume that we have a decider for this language. We're going to assume that it is decidable. And then we're going to use it to construct a decider for the acceptance problem of Turing machines. This construction gets a little bit more complicated, so we'll see that another example of the technique of reduction that's a little more complex. But if we were able to construct a decider for the acceptance problem for Turing machines, that would be a contradiction. So our assumption that the emptiness testing of Turing machines is also undecidable. Okay, so what we're going to do is we're going to reduce the acceptance problem for Turing machines into the emptiness problem for Turing machines. So this is an outline, and now let's look at the whole proof in more detail. Okay, it's easy to get lost in this, but remember what we're doing. We're trying to give an algorithm. We're trying to construct or show an algorithm which will decide the acceptance problem for Turing machines. Okay, this algorithm takes as input a string, and it decides whether the string is part of the language. The string is an encoding or a description of a Turing machine and an input to that Turing machine. And if that Turing machine, when run on that string W, would halt and accept, then this algorithm that we're trying to construct must also accept. Otherwise, it must reject. So our algorithm that we're building is given M and W as input. So the algorithm has two steps. The first step is to take the Turing machine and M and modify it a little bit. We'll call the modified machine M prime. Okay, keep in mind that we're not going to run this Turing machine M or M prime. These are descriptions of Turing machines. Okay, and we're providing an algorithm S. Okay, now remember that algorithms are given in the form of Turing machines. So what we're doing is we're constructing a Turing machine which will decide this language. That can get a little confusing, so I prefer to say that we're constructing an algorithm, okay, S, which is given the description of a Turing machine M and a string and does some stuff and either accepts or rejects. So the first thing it does is it takes the Turing machine M, whose description is part of the input, and it modifies that Turing machine a little bit. It doesn't run it, it modifies it. And we're going to denote the new modified Turing machine M. And remember this, our algorithm is also given W as an input, the string W. Okay, so we've got W within algorithm S as an input, so it's essentially fixed. Okay, so when we construct M prime, okay, we're constructing it given M and W, so W is like a constant. We already know it. Okay, M prime will take an input. It's a Turing machine after all. It's going to take some input. So we'll call the input to M prime X. And so what does M prime do? First of all, it rejects all input strings X that do not exactly match W. And then it may or may not accept W. If X is not W, if the input to M prime is not equal to W, then M prime will immediately reject it. Okay? The only thing that it might accept is a string X that happens to be equal to W. So if you give M prime W, it might accept it or it might not. It may or may not accept W. Okay, so if machine M prime accepts W, then the language of M prime consists of simply one string, W itself. But on the other hand, if M prime does not accept W, then the language of M prime is the empty language. In other words, M prime does not accept anything. So M prime either accepts one string or no strings. So the language is either empty or not empty. And here's the algorithm for M prime. Okay? First of all, algorithm S constructs this new Turing machine M prime. And what that Turing machine does is it first takes its input and checks it against W. It compares it to see whether its input is W. Remember, when S constructs this Turing machine, W is an input to algorithm S along with M. So W can be treated like a constant, and we can create code to compare the input on the tape to W, and if they are not equal, we reject. So in this way, any input to M prime that is not equal to W is rejected and not in the language. And then what M prime does is it includes M as a subroutine, and it just runs it or simulates it on X. Right? So remember, S is constructing Turing machine M prime. It's not running it, it's constructing this Turing machine. Okay? And M prime first checks its input to see if it's W, and if it is W, then it simulates M on X. It passes control to M. So we include the description of M in the description of M prime. We have, algorithm S has a description of Turing machine M, and a bunch of states in machine M, and those states get added to the machine M prime that we're constructing, along with some states to do this initial check first. And then if M accepts, M prime will accept, of course, because we're just simulating it. And then if M rejects, then M prime would reject. And if M loops, then M prime will loop. Remember I said that the algorithm for S had two parts, step 1 and step 2. So let's look at the whole algorithm for S now. And what we're doing is we're constructing an algorithm to decide the acceptance problem for Turing machines, assuming that we have R, which is a Turing machine to test whether a machine accepts anything or not. So algorithm S has two inputs, the description of a Turing machine and a string. And in the first step, it constructs M prime, a new Turing machine. So how does it do it? Well, as I said on the last slide, it uses M. It adds a test in front of M to see whether X equals W, and if it does not equal W, then it rejects immediately, but otherwise it passes control to M. So that's how algorithm S builds M prime in step 1. Note that if the language of M prime is not empty, then that means M would accept W. And if M accepts W, then the language is not empty. Otherwise, if M doesn't accept W, then the language of M prime is empty. So in step 2, we use this hypothetical algorithm R, which will decide whether a language is empty or not. Okay, we use this hypothetical decider to decide whether the machine M prime would accept anything or not. Is the language of M prime empty or not? If R accepts, then it means that language is empty. So the language of M prime is empty, meaning M does not accept anything. Sorry, it means that M prime does not accept anything, which implies that M does not accept W. Okay? So if R rejects, it means that the language of M prime is not empty, and that can only be if M accepts W. So we can decide the acceptance problem for Turing machines. Okay? If we have R, so we have built a decider for the acceptance problem for Turing machines. But of course we know that that can't exist, so this is a contradiction. So our conclusion is that testing for emptiness of a Turing machine is itself undecidable. And that concludes the proof.